Hi, I'm going to talk about intersections, and this video also, this problem also uses the dot product. I just decided to do on the side of the other ones, so I could shorten that one. So the base case that I'm going to use to talk about this is the intersection between a line and a plane. So I have here a line, this dotted line, and I have a plane with these this cyan bar. They are both defined by a position. So I have line position and plane position, and a direction. So I have here the line direction that goes along the line, and I have the plane normal that is perpendicular to the plane. In the case I'm given a line by the means of two positions, let's say this one and this one, I can always do a delta, and this will give me the line direction. So how do I solve this? How do I find the intersection between these two subjects? Intersection is basically a position or a point that belongs to both of them, both to the line and the plane. And so the first thing to do is to do a delta between the line position and the plane position. So this brown vector here that goes from line position to the plane position. And if you notice, basically, let's say that instead of having this direction, let's say that the direction of my line was like this. In this case, I would have my problem solved because, well, the intersection between this line and this plane would be the plane position itself. Well, it is not my direction at the moment, but I can still use this as a reference. So in this case, well, there's an intersection, and I'm going to use that to basically scale this vector because I know whatever position is along this line, it can be reached by a scaled version of this vector. So this intersection here can be reached if I scale this vector by a certain factor. There's a certain factor by which I can scale this, so it becomes this, and that's what I want to find. So let's look at something that I'm going to use to talk about the mindset of solving this, even though I'm not going to use it exactly as it is in the end. So I'm going to talk again about projection that I've shown in the other video. So let's say if I have this vector here and I have this vector here, and I want to project this one onto this one. Basically what I do, since this is the direction into which I want to project, I normalize it. And so I normalize this vector, I get this small unit vector here, and then I do the dot product between this and the normalized version, as you can see here. And this will give me a coordinate. Right? I get this coordinate here, and this coordinate will allow me then to scale this vector and get it to come up to here, and then I can say, well, I projected this vector onto this direction. It's this vector here. Now, what I'm interested is not the vector so much, but the coordinate, this part here. And so let's look into that in our problem. So I have this line plane delta in the context of the line position. I have the line direction also in this context. And so I'm going to place a copy of the plane normal in here so I can demonstrate what I'm talking about. So I want to project the line plane delta and the line direction onto the direction of the plane normal. So to do that, let me just draw here a line. I'm going to just pass some perpendicular line to that, and this is going to give me a certain coordinate value. In this case, I'm just going to call this coordinate, just call it, in this case, reference, because I know this is an intersection, and I'm going to use it as a reference. And if I do the same thing for the line direction, I get another coordinate, and this will be W, like in what I have. And so I see there's a difference, right? These are different coordinates. This is where I want to go to, and this is what I have. And the question is, why do I want to go? I want to scale this to become that. Well, because you'll notice that even this position here, if I project it onto this line, I get the same coordinate, or any other position in the plane projected onto that line will go up to here. So having this coordinate basically means in this case that it's something that is in the plane, and I want to get there. So I know that if I multiply something, if I multiply what I have by some factor, I'm going to get to my reference. So if I put this in the order of the factor, I get that my reference over what I have is going to give me that factor. The same will be true if I just apply the dot product. So I'm not going to use projection, as I mentioned. I'm just going to use the same, in a way, the same structure. So I'm going to do a dot product between the position normal and the line direction, and the line plane direction and the position dot. And I'm going to divide them. So on top, I'm going to say here, on top, I'm going to have my reference. So I'm going to have a dot product of my plane normal with the line plane direction. So this is my reference. Then I'm going to do the dot product of the plane normal with the line direction, which is what I have. Great, so this here will be equal to the factor by which I have to scale the line direction to get to my solution. So this here is congratulations, you got what you wanted. Right, then to that position, if the context in which I'm working on is, say, the world context or something like that, let's say that my context is here, and so I have here the line position. Then afterwards, I have to add this position. So I have to add the line position to my solution. And so these two together, if I connect that, is the position that I want. Okay, so let's look at this working in layout. Here I have two objects. Object A is holding a line and object B is holding a plane. And I have some visual elements to kind of represent the direction of the normal of the plane and the direction of the line. And in this object here, I have a nodal motion that has two compounds. And I'm going to look into the first one because it addresses what I was talking about there in the drawing. So the first one is called Intersect, Line, and Plane. And it has 4 inputs: line position, line direction, plane position, and plane direction. And for those, I'm going to use object A and object B. For the position, I'm just going to use the position output. For the direction, I'm going to use both objects' forward output, which is basically in this case their local z-axis. So if I come here to the scale transformation, you can see the scale handle is pointing in the same direction as those arrows that I've placed in there as a display gimmick. And so let's look inside, see what are the operations here. So first off, I put the plane position in the context of the line position. So basically I subtract the line position to the plane position, which is basically to get this brown vector here, the line plane delta. Then afterwards, I have 2 dot product operations. Both of them have the plane direction in them. So that's why here you can see that in both of them I have the plane normal. And one uses the delta, the other one uses the line direction. And so the result of those 2 dot products are then put into this divide. So on top goes the dot product that uses the line plane delta, and on the bottom uses the line direction of the vector, the line that I have. So just like I've mentioned here. So that factor is then used to scale the line direction and add onto the line position, and that's basically the whole thing. Just like I mentioned here, where I add the line position plus my solution, and I get my final position. So let me connect this here. Of course, visually I've made all these visual cues, and we can all certainly know that the position should be around here. So if I put this in here, you can see that there's where the position where the line meets the plane. It's a position that belongs both to the line and to the plane. And so this is a nice solution because, it's not any raycast or anything. It's an abstract solution. So even though you can be, here the polygon ends, there's nothing more to, if you were raycasting, this would have nothing to raycast on. But with this, it keeps going on. It's just an abstract plane. It's not exactly raycasting to a specific geometry. So you can see this go. Of course, you can also rotate the plane. You can see it sticks to that. And so this is it. I also have an output called rotation. And this rotation allows me to orient the allows me to orient the object with the plane. So here I have basically, I'm going to talk about later. So here I have matrix to Euler angles, and I'm going to talk about this in the next chapter. And I also have cross product here to find perpendicular vector x. You might want to take this one out if you want to disconnect. Depends on what you want really, but. So I'm going to talk about cross product in another chapter, but cross product is basically when you have 2 vectors and you want to find a vector, say like this, and you want to find a vector that is perpendicular to both of them. So this vector is perpendicular to this one and perpendicular to this one as well. So this is what the cross product is doing there. But yeah, don't mind much the rotation part. Here I'm just worried about positions as of now. So let's look into the other compounds, a bit more complex, and basically it possibly performs three operations. This one, as I've shown, and other two. So if I click the node, here I have some comments. It says operation 0, it will give you the intersection between two lines. So when I put 0 here in the operation input, I'm going to get the intersection between two lines. If I put 1, I'm going to get the intersection between two planes. And if I put 2, I'm going to get the intersection between a line and the plane. So this last one is just the same as we've seen here. So at the moment, I have 2 being used here. So I have the same thing as this. And so if I come here, disconnect this, type this here, I'm going to get exactly the same thing, right? And let's look into the internals of the compound. The algorithm is basically the same. The subtract, dot, divide, add scale. This part is the core is the same. So if I come here, so it's a bit more confusing because there's a lot of decisions being made, but in the end, the core of the algorithm is the same. Subtract, dot, divide, add scale. So it's exactly the same thing. The only difference is because sometimes so basically what I'm using here is the line plane intersection. It's just that there are some decisions with some cross products here being made so that I can have the line be considered as a plane and the plane considered as a line in a way. Let's look into the why of that. So I mentioned that the cross product gives me the perpendicular to two vectors. And so let's say that I have this line direction here, and I basically turn it 90 degrees, but not any 90 degrees, but 90 degrees relative to a vector that is perpendicular to both. So again, I have, let's say I have the plane normal, and I have the line direction, and I find a vector that is perpendicular to both. Let's say now that I turn the line direction 90 degrees about this axis here. So something, instead of looking like this, it's gonna look something, say, like this. What I do with this is the solution that I find between this line and this plane will look a bit like I'm dealing with two planes. Or if I turn the plane direction by 90 degrees, something like this, the solution that I find between this and this, it's like I'm finding the intersection between two lines. So with these turns on the direction of the line and the normal of the plane, I can kind of simulate that they are something different. And this can, if I draw it in here, I think maybe it gets more clear. So if, let's say, I come here and I do this. So what I'm doing here, it's passing a line that is perpendicular to my initial line. So let's say that sort of I rotated it 90 degrees, right? Now, instead of having this intersection here, I'm not going to get this, but this intersection here with the plane. So in a way, this is going to, this line direction is not behaving anymore as the direction that goes along the line, but as a plane normal. So it's perpendicular to this line here. So it behaves just like this one, that is perpendicular to a plane normal. So instead of this intersection, I find this one. Okay, let's look into the other case in which I turn the plane 90 degrees. So let's say I come here and I turn my plane 90 degrees, or at least the description of its direction, because that's what is to it. And so instead of this being something that is perpendicular to my subject, is something that goes along the direction of my subject, just like the line direction goes along the line. So now this behaves like a line. And what intersection will I have? Well, not this one, but this one. And so now I have the intersection between two lines. So this is what these cross products are doing here. Just basically switching things around so I can have outputs that are used for different situations. So let's look at the other two. And as I change them, so let's say here that I come here and I change this to, let's say, so 0 is 2 lines. So I'm going to change this to 0, and now it's going to give me the position where the two lines intersect. And I have here some switches. Let me move these two closer. And you can see that, let's say, if I want to switch these two into lines, so I have these two switches that allow me to change something from a line to a plane, or from a plane to a line. And so in this case, I want B to become a line, so I'm going to put it to the right. So I'm just going to reset it. So now I have 2 lines. And you can see that those 2 lines intersect there, right? So if I rotate this, see that they go to that intersection. What if I put, let's say, I want them, both of them to become two planes. So both of them become plane, and I come here and I put two planes. I have to have one in the operation. So I'm going to put one in here. And okay, so I'm going to rotate this plane, and the shading, the transparency shading, it's a bit tricky. So I'm going to turn this to 0. Okay, so now it becomes a bit more obvious. And so you can see that now the object is constrained in the intersection line of these two planes. So in this case, I'm using this as a constraint, as a motion constraint, but you can definitely use this as an intermediary calculation where you just, well, I need to solve this problem, but to solve it, I need to find the intersection between this and that so that I can use it for something else. And you can use one of these compounds, or you can pick, a simplified version of all this to basically perform that calculation and solve your bigger problem. Right, so this is just an example to show that the same thing, the same algorithm can be used to solve different cases. Now, just to finish off, I think I just wanted to show what is these two factors here. And so let me transform these two into lines. So for that, I'm going to reset this. And so we have a problem, let's say, with lines is that, well, they might not intersect in the same, they might not intersect, they might not be coplanar lines, meaning they might not exist in the same plane. And so, of course, it becomes a little bit hard to understand, well, where's their intersection point? They don't touch. Now, these two lines are not touching. So let me put this here to 0. So these lines are not touching. What can I do? So let's look into that here. Sorry, and here. And so have two lines that are on different levels, but I know that for both lines, there's a point that is closer to the other line. So here, let's say that I know that this point is a point where that is closer to the other line in a straight line, and the same for this one. So it's not the same as this, or as, let's say, this. So this one takes more, it's a bigger distance, or this one is a bigger distance, etc. And so these two lines, you kind of have to imagine them in 3D. They are not just something that, that is converging here to a point. It's more like this one is oriented on the x-axis, and this one is oriented on the z-axis, for example, if it helps you thinking about it. And so we got a problem. They don't actually intersect at a point, but we can find these two positions, and then we just have something to decide. Do I want the solution to be this position? Do I want the solution to be this position, or something in between, right? And so this is what the AB position means, is that I'm going to decide, along this vector here, what is going to be my position. So in this case, I have it set to 0. So basically it means it's going to stay on the position that belongs to A. If I set it to 1, it's going into the position that belongs to B. If I set to 0.5, which is actually the default value, so this port here has a default value, it's going to be in something in between. And the same will be true for the orientation. So here I have this rotation output. If I put it like this, at the moment it's being oriented as this as object B, because I have, let's say, I have 1. So it's taking the orientation of the subject B. If I put 0, it's going to take the orientation of subject A. If I put 0.5, which is also the default value, it's going to be something in between. So if I come here and I do this, you notice that is like a bisector angle. So something that is in between those two directions. So this is it. Kind of sums it up what I wanted to talk about intersection. Still another application for the dot product, and sometimes a need to solve some geometric problems.